my last class, I recorded it to the cloud, which works, but I prefer having my own video on my computer instead of, plus when I put it in the cloud for UT Tyler Canvas, eventually that link and the video expire in like 2 years. Everything lives forever on YouTube, unless you violate copyright. But as I was saying, in the past, I said, all right, if there's a COVID absence or something that merits having a Zoom session, I'm going to run a Zoom session. Otherwise, I will conduct it like I did pre-COVID, where I just write notes on paper on this overhead projector and then scan them and put them in Canvas, or at least hope I remember to do that. But I realized that it was actually a bigger strain on me to constantly go back and forth between the two, and probably a bigger inconvenience for you to wonder, all right, is he going to write or is he going to open up a Zoom session? So to err on the side of caution, I will just conduct a Zoom session each class day except test days. For obvious reasons, we don't need a Zoom session on the test day. And even if there's nobody joining it, at least it will be recorded so that you can catch it later. The disadvantage to catching it later on a Zoom session versus the notes that I write, the recording is going to be an hour plus long. And when I write notes, it's like 5 or 6 pages. So it's a lot longer to try to troll through a recorded Zoom session to find anything that you missed, as opposed to just reading the notes that were scanned and uploaded. But at least it has an audio component to it, which is more than I can say for when you write notes. Okay, what is this? Oh, okay. All right. All right. So we're going to get this thing started. Let me get everything. This is Math 1340. I'm such a G. Math 1314-01. Today is not Monday. I keep wanting to make today Monday. I don't know why. Wednesday, October the 13th. Yes. Yes. Okay. All right. So let's get this thing started. All right. So again, concerning the class that we did not have on Monday, and not getting too terribly far behind, I did post the following announcement about class notes. I'm sorry, here it is. Video, homework, and quiz for section 8.1. This was posted on the 6th, which was a week ago. Yes. In preparation, because the next morning I was up and on my way to Galveston, but trying something a little bit different. I literally copied what I had used when I taught this class online, the module for section 8.1, and I realized, hey, there's a lot of nifty things in there that I could use again. That was the whole purpose of creating it the first time, so I could use it in the future. But it was a list of, here's what you need to be able to do by the time we get to the end, and then a bunch of videos, and then a PDF of the homework problems, and then a quiz over that homework. And that's exactly, also plan to cover more of section 8.1 on Wednesday. That's today. I do plan to use the homework and quiz included in this module. As such, you're welcome to move as quickly through it as you like. 2 comments, audio quality is not too good because when I made these, I didn't have this headset. And it says right now the quiz is due this Friday. I might change that due date. But I did ask you to come to class prepared to discuss section 8.1 and ask questions over the homework. So if you go to this module, and this is what every single module looked like when I did this class online, it started with a list of, all right, here's what you need to know by the time we are done with this section. Now it says by the end of this week, but it's really by the end of the section. Oh, it was this past spring. Be able to do these things. And I just thought it'd be kind of neat to let you know in advance in an online class, this is what I expect you to be able to do when it's all said and done. And actually, the reason I made this list of learning outcomes, which I'm going to download just so I can view it outside of this frame, inside of a frame. I hate framed frames inside of a website. But the real reason I made this wasn't for my students. It was for me. It was to make sure that when I make my videos, I say these things. So it was my script, if you will, or at least a skeleton version of my script. All right, make videos, talk about these things. And then, but also this module, let me go back to it for a second. Video about the F distribution. Excuse me, it's not the F distribution. It's the actual F. It's not a video. It's the actual F distribution itself, which I still didn't print for you. And then just a little title saying, all right, here we go. Video, 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 homework. And I did handcraft all of the homework assignments so that I made sure that the videos covered the things that I wanted them to. And I have handcrafted homework assignments for the rest of the class. I thought about using them with you guys, but it would almost totally defeat the purpose of having access to the textbook in the first place. I might in a crunch, but I don't think I'm going to. But here's all of the homework problems. Use the F distribution to look up those. Determine which set provides stronger evidence of different population means, et cetera, et cetera, et cetera. And, you know, the homework goes on and on. There we go. And then, go away, you bother me, thank you. Then there was the quiz. And I thought, well, I already got a quiz written. Why don't you guys do it? And right now the due date is on the 15th. I'm going to change that right now. Don't worry, I'm not going to change any content. I am going to make it due, let's see, I think maybe Monday. I don't want to let it go too long, but at least that way it gives you a chance to come back and ask questions one more time. So now it's due on Monday of next week instead of Friday this week. Okay, so, but that module is already there, and I'm not going to take the easy way out and just say, well, here's the next one and move everything over from when I taught this class online. I just forgot that it was there in case I needed some backup if we don't have class. All right. I'm not going to ask the question who has watched any of the videos because I'm afraid how many people would not raise their hands. But I will ask if anybody has any questions over the homework. So let me open it up. Yes, Jeffrey. Okay. You mean the video didn't help you get these answers? Mm-hmm. Oh, I see the problem here. Look at that. That says SSG and SSG. Now, some of you may not know what that means, and that's okay. But if you read this whole sentence, you can probably figure out what I meant to type. And I'm not sure if this is where you had your particular question, but this should have said SSE, right? Because it says the values of SSG and SSE were calculated as these. Well, the second one should have said SSE, but I get the feeling that's not really what your question or concern was. Mm-hmm. Well, if you have SSG and SSE, then you got to complete the ANOVA table to get to the test statistic. And if you don't know what that means, don't worry, I'm going to illustrate all that in just a moment. But to arrive at the desired answer, and the reason I say this is because the process to calculate the test statistic, because we're just doing a hypothesis test, the process to calculate the test statistic involves a lot of calculations, including 1, 2, 3 divisions. And when you divide, you usually get nasty decimals, which requires to do some rounding. And so to get to the answer that I was hoping you would get to in the quiz in Canvas, it says round your answers for both MSG and MSE to 2 decimal places before calculating F, which you should also round to 2 decimal places. But is your question how to get to the test statistic based on this information here? Okay, so we got to work up to that, and we're going to work up to that because if I jump into it cold, you might follow it, maybe a couple more, depending upon how many watched all the videos, and kudos to you for watching all the videos. But there's a lot between the beginning of this section and this. which is kind of evident because this is the end of the homework and there's a lot prior to that. So my goal is to get to answering your question because it's really pretty straightforward. Okay. Does anybody have any other questions that you'd like to ask, just in general or specific? Yes, Lindsay. Mm-hmm. With the I? It's 40, right? And I want to use this particular question to kind of explain what's going on here. And then we'll get back into the details. An ANOVA test, an analysis of variance test, attempts to answer the question, do these populations possibly all have the same means? Or is at least one of them different from the others, or at least two of them not equal? And so when you conduct an analysis of variance test, you're gathering samples from multiple populations. And in this table that you see here, there are three populations that we're sampling from. You can tell because we have sample A, B, and C. For the first population, we sampled 12. We calculated the mean of that sample. It was 334 and its standard deviation was 9.4. For the second population, population B, we took sample B, have a sample size of 11. Excuse me, that got recorded. Sample size of 11. The sample mean from that sample was 42 with a standard deviation of 6.7. And then for the third population, we took sample C. We took a sample size of 10. Its mean was 45. Its standard deviation was 10.4. But what this grand thing here is, when you talk about a grand sample size, a grand sample mean, and a grand standard deviation, it's because there is a grand sample. And what a grand sample is when you forget the fact that these three different samples came from three different populations, and you just treat them as one gigantic sample from one gigantic population. In other words, you dump all your samples together and recalculate everything. The grand sample size will always be the sum of the individual sample sizes. That makes sense. We take 12 from this population, 11 from that population, 10 from that population, put them all together. Look, 33 people in our grand sample. Now, as far as calculating the grand sample mean of the grand sample standard deviation, there is a way to calculate them from the individual samples. Let me redact that. There is a way to calculate the grand sample mean. In other words, what's the average if we dump all the samples together from the information that's here, but it's not as straightforward as just saying, let me average these. You actually have to do what's called a weighted average, but let's not get into that right now. And calculating the standard deviation of the grand sample, if we were to dump all the samples together and blur the lines between who came from what population, there's not a straightforward way to take these samples, individual standard deviations, and then calculate, all right, well, what's the standard deviation if we dump all these samples together? You would just have to recalculate it from scratch. Trust me, I've tried to come up with the formula that says, how do I take the standard deviation from my individual samples and use it to calculate the standard deviation if I dumped all the samples together at the beginning? And it got to the point where I was like, forget this. We'll just calculate it manually without worrying about what the sample's individual standard deviations were. But your question about this X bar, you all should know by now that X bar means sample mean. My stats 1 class, some of them still don't know that. And on their next test, they have a matching portion where they have to match the variable name to the variable. And some of them are going to miss it. And I'm like, you get to stats 2, forget it. You just got to know that X bar is sample mean. But in analysis of variance, where we have multiple populations that produce multiple samples, which produce multiple sample means, those individual sample means are subscripted to say first, second, or third sample. Or in this case, it'd be A, B, and C. But when you see an X bar without a subscript, it is not referring to a specific population sample, it's referring to all of the samples as a big, gigantic sample. So in this formula, yes, this X bar is the grand sample mean, so it's the 40. Okay, now there is one other thing that I want to apologize about. I had forgotten I had done this until I saw what I'm looking at right now. Remember how I complained that this author says, let's not worry where all these values come from. We'll just give them to you, and I want you to move forward. I took it upon myself when I made the videos for this class online to go through how do you get to these values. The formula for SSG is this nasty thing. It's not really that bad. All this says is for each sample, you take its mean, subtract the grand mean from it, which measures how far off from the population is this sample, square it because that eliminates the chance of things canceling, multiply it by the sample size, and then you do that for all the different samples and add them up. And then the same thing here for the SSE, which I haven't told you what that means yet. You, for each sample, you square its standard deviation, which actually gives you variance, hence the name analysis of variance. And then you multiply that times the sample size minus 1, which is the degrees of freedom. And then you add up those three. And then for SST, which stands for SS total, you just do this. Now notice that none of those variables have subscripts, which means they are not referring to individual samples. Hence, they are referring to the grand sample. N is the grand sample size, which is 33. S is the grand sample standard deviation, which is 9.9. And then you can calculate all those values. And then there's a follow-up question about the fact that these two answers are supposed to add up to be this one, but they don't exactly. And it has to do with rounding errors. So yeah, there's a lot going on in the background. On your test, I will probably not ask you to do these formulas. Okay. They are time consuming. Okay. I will probably just give you the values because you can notice the question that Jeffrey asked me. And again, I haven't told you what all these things mean yet, but in the values that, well, look right here, and you may not know it, but this is the SSG value because it's SS groups. That's what the G stands for. And I gave you the SS total. Didn't give you the SS errors, but there's an easy way to calculate that because this column is additive, meaning that the first two numbers add up to the third one. Well, the minute I tell you that, you probably know what goes in this box right here. The top two numbers add up to the third one. Top one's 1,000, third one's 5,000. What goes here? 4,000. Yep, it is that easy. So it is a nice relationship between this column, top two add up to the third one. So in practice and in most of your homework, well, in the book homework questions, they actually give you these values instead of asking you, all right, go calculate them. But being the theoretical math guy that I am, I enjoy knowing where some of these numbers come from. And then, well, I kind of force you to do them as well, briefly. But on your test, I will not ask you to manually calculate these things. This is just so you can get a feel for where these numbers come from. So temporary annoyance, but then they'll go by the wayside later. When you need the values for these, whatever they represent, because we haven't talked about that much yet, I will give them to you either inside of a table like this, or I will tell you in the midst of a problem, assuming that I put the correct letters here. I will just give you those values, bypassing the need to calculate those sums. Now, if I remove the need to calculate those sums, this is a very straightforward and fast process. We just got to figure out how to put all the pieces together. I am going to ask the question, how many of you watched any of the videos? My apologies for having low expectations earlier. I say that because in another class at TJC, when I asked who had watched videos, half the class looked at me and said, "What videos?" One had watched them, which put us further behind. So thank you for those of you who watched them. And if you didn't watch them, it's okay. I don't think any less of you. All right, so what I would like to do today is kind of explain what the heck is going on here. And I think I might actually just use this homework assignment as motivation as examples, if you will, AKA work these problems to explain what's going on and how to do it. So it's a little uncharacteristic of me to work your homework problems before you take a quiz over them. Well, in this case, after for some of you. But I mean, it's a perfectly good thing to move the process forward. So we're going to do that. All right. So let's begin. And I should probably write some of this stuff down in the whiteboard in Zoom. So we're going to do that. All right. So we're going to wrap up the discussion about analysis of variance and ANOVA. And remember, this is for testing multiple population means. And I want to remind you what we did talk about last time. We are doing a hypothesis test. And so as a consequence, we start by stating hypotheses. The null hypothesis is always of the form, all population means are equal. But it can also take a different form. It can also be of the form, there is no association between something and something. I'm going to put that on a new line. And the example I gave last time was, should your ethnicity matter when it comes to salary? And we would hope the answer is no. But if I pose that as a null hypothesis, for example, if I said the null hypothesis is there is no association between salary and ethnicity. The reason that gets to be the null hypothesis is because what we're insinuating is if we say, what's the mean salary for, I'm going to put C for Caucasian, and we look at the mean salary for African Americans, and we look at the mean salary for Hispanic, and whether or not these are actually categorized as ethnicities, let's not split hairs like that. And let's say the mean salary for Asians, I'm just going to put A for Asians. Now, of course, you would need to define what all of these subscripts mean. If there's no association, then these mean salaries should be the same. In other words, if your ethnicity does not have an impact on your average salary, let's say at a big company that hires globally, well, hires within America, but hires people of all ethnicities. If your salary truly is independent of your ethnicity, then all of the average salary should be the same. So that's why the null hypothesis could also be stated in terms of a lack of association, because your ethnicity shouldn't affect whether or not your average salary, the average salary for this group is different than the average salary for that group. So you can form the null hypothesis in two ways. You can literally say this mean equals that mean equals that mean equals that mean. You can say all whatevers are equal, all average salaries are equal across all ethnicities, or you could state it in the terms of the lack of an association. There's no association between salary and ethnicity, or those are independent of each other. One shouldn't affect the other. Now, clearly your salary can't affect your ethnicity. It can't be like you got a raise and suddenly you belong to a different ethnic group. But it could be, oh, you belong to a different ethnic group, so you don't get a raise. Yeah, that's a lawsuit waiting to happen. Now, the alternative hypothesis, well, there's a lot of ways to talk about the alternative hypothesis. Is always one of the following. You can say at least one mean is different. And you could also say at least two means are different, meaning that this one doesn't match that one. But saying one is different means it doesn't match somebody else. Well, I stand corrected. I don't think we can say that. And here's the reason I'm pondering that. let's say that, and this is totally, that's not what I want to do. This is totally concocted, but I don't think I can actually say that. So I'm going to change that, because what if we had mean 1 equals mean 2 equals 10, and I'm sorry, mu1 and mu2, and mu2 and mu3 and mu4 are equal to 20. Is at least one mean different? Is this different? Different from whom? Well, he's not different from that person. Is this guy different? Well, he's not different from that one. So it's possible that all these means are one thing and all these are another, and no one is truly different than everybody else. So maybe I should phrase this a little bit differently. I am going to rephrase it. Instead of saying at least one mean come back, instead of saying at least one mean is different, I'm going to say at least two means are different. That way we can't have this, well, we all match and you all match, so everybody is the same as somebody else, but at least one of us is different than one of you. So we can say the alternative is at least two means are different. And we could write it symbolically, but writing it symbolically is a little bit trickier because you don't know which two means are different. The classical way of writing it using muse is, I wouldn't write this down because I'm not going to ask you to do this, but just to show you. In other words, the alternative version of the one in red down there would be mu I is not equal to mu j for some I and j. In other words, there's a couple of subscripts so that their averages are different, but that really gets a little bit more on the technical side of things than I would like to get on. So we'll say that the alternative will always be at least two means are different, or you can put it in context, at least two ethnicities have different average salaries, or you could state it in terms of an association. There is an association between ethnicity and I missed an N in salary. Because if there is an association, then your salary should be different depending upon your ethnicity, which means that at least two of the means are different. So it can be generic or we can be specific and put it in context, but those are the two ways to state the alternative hypothesis. At least two means are different, or you could say there is an association between ethnicity and salary. Whichever one you use, make sure you're consistent. So for example, don't say your null hypothesis is all population means are equal, and then your alternative is there is an association between this and that. Be consistent in the wording of your hypotheses. All right, so like I said, it's just a hypothesis test, and we also talked about the F distribution. Now, I don't have the F distribution pulled up yet. I'm about to fix that. Give me 1 second. Go back into Canvas, go into Files, go into Distribution Tables, click on the F distribution. Why is it in here twice? They're the same. Doesn't matter. We'll pop it open in a separate frame. Okay, and now let's go back to the whiteboard. Okay, so, but yeah, the next order of business in a hypothesis test, if we're using the critical value approach, is to find the critical values and the regions. Values and regions. But we had talked previously about using the F distribution, and I'll remind you how it works. But first, I want to remind you that an ANOVA test is always right-tailed. So we don't have to worry about that. And we're going to use the F distribution. There's supposed to be a comma and a space in there, which requires 2 degrees of freedom, or 2 different degrees of freedom. And those degrees of freedom are usually referred to as degrees. I'm just going to put DF for the numerator and degrees of freedom for the denominator. That's supposed to say 4. Denominator. And these both have formulas, and I think I might have given you all the formulas before. The formula for degrees of freedom for the numerator is k minus 1, and the formula for degrees of freedom in the denominator was n minus k, where k is the number of groups, which is the same as the number of samples, which is the same as the number of populations. And n is the grand sample size, which you can also think of as the sum of the individual sample sizes. So there's a couple of ways to think about that. I think I can fit all that in one line. I can, look at me. All right, so for example, just to remind you how the F distribution works. For example, find the critical value if find the critical value at, we'll say 2.5% significance. We don't use that one too often. We'll use it now. If, we'll say K equals 5, so we're sampling from 5 populations. And N equals, we'll say 40, meaning that our 5 samples have a total sample size of 40. Well, we just got to calculate the correct degrees of freedom. Degrees of freedom for the numerator would be K minus 1, so 5 minus 1, which is 4. And the degrees of freedom for the denominator, that's a horrible spell, would be N minus K, so 40 minus 5, which is 35. So we go to the table, and let's go look at the table. All right, remember, this table has multiple pages because you have to, you have 3 parameters, so to speak. You've got 2 multiple different degrees of freedom and a significance level. This table is set up 1 page per significance level. So first you pick the correct page based on the significance. We're doing 2.5%, so we would go to that page, which should be the 3rd one. And once you go to the correct page, then you go to the correct column based on degrees of freedom for the numerator, which is 4, and based on degrees of freedom for the denominator, which was 35. So we're going to the 4th column down to the 35th row. Please be on here. There it is. 3.1785 is our critical value. Does anybody have any questions about why I'm highlighting that number? Correct page, correct column, correct row. It's a 3D table, if you will. 3.1785. Okay. All right. So F is 3. I think I said 1785. Is that what I said? Okay, 3.1785. So if we were to draw the picture, it's like the chi-square distribution in the sense that it starts at 0. And then it's always a right tail test. So this would be our rejection region. Our non-rejection region would be here. And our critical value is 3.1785. So again, it's just a critical value move. Different table, requires 2 different degrees of freedom, each of which have their own formulas. And then when you go to the table, you go to the correct page based on the significance level, the correct column based on the degrees of freedom for the numerator, and the correct row based on the degrees of freedom for the denominator. Any questions about what just happened there? Okay. I'm just going to back up a page. I forgot what I wrote. Talked about critical values and regions. Okay. Where we left off, though, I believe was the calculation of the test statistic. I don't think we calculated it. I think I talked about it briefly, but we didn't actually do it. So here's the new stuff. The test statistic, in a word, is messy. The final formula for it is pretty easy. I'm not going to waste your time looking up the formula chart I gave for this class last time. I will make it available to you eventually. But the way you calculate it is you complete what's called an ANOVA table. Now, I'm going to leave out some of the method behind the madness about what these things mean and where they come from. Remember those sums that I showed you? I said, oh man, these are nauseous, but I'm not going to ask you to do it on the test. I'm going to kind of bypass where those come from and just show you what an ANOVA table looks like. I'm going to draw it generically first, and then on the next page, we'll do one specific for an example, probably something from the homework. The way an ANOVA table looks is it starts with one column. It's going to have more columns. It starts with one column in 3 rows. The first column is for degrees of freedom. And the first row is for groups. The second one is for errors. And again, I'm kind of bypassing what these things actually mean for the in the short term, maybe in the long term. And the third row is for the total. Now, there are formulas for all of these. And what I'm going to do in this version of the table is just show you what these formulas are. I've already shown you the degrees of freedom for groups. It was K-1. I didn't call it degrees of freedom for groups, but it's the same formula. The formula for degrees of freedom for errors, that's the same as the degrees of freedom for the denominator. Saying groups and errors here is more specific to the context ANOVA, but in general, in an F distribution, you have a degrees of freedom for numerator and degrees of freedom for denominator. So calling them groups and errors here is specific to doing an ANOVA problem. Using F for a different context, you wouldn't say groups or errors there. Now for the total degrees of freedom, it's just, it's the sum of those. Now I know those are algebraic expressions and this isn't an algebra class, but does anybody know what you would get if you added K-1 with N minus K? Hint, there's some like terms. You could say -1 plus N, or you could say N minus 1. Because if you added those, the K's would cancel and you'd be left with the N and the -1. It is worth pointing out, and I'm going to type this so that it's a little bit legible, but I'm going to type it in a smaller font size, that this column, DF column, is additive. I'm going to shrink this text box to make a line, force a line break in it. There it is. But the degrees of freedom column is additive, meaning that the top two add up to the bottom one. That's why the bottom one's called total. The total is the sum of the two above it. So, which means if you know two of those, you can find the third one. If you know the top two, you can add it to find the third one. If you know the bottom one and one of the two above it, you can subtract to find the missing one. All right, so that's the first column in an ANOVA table. The second column is titled SS. And the abbreviation SS stands for sum of squares. It's a reference to the formulas that crank these things out. I want to switch back over to the homework assignment just for a second to remind you what those formulas look like. You probably don't need to write them down. All right, where's the homework assignment? Nope, there it is. Those formulas are fairly obnoxious, but if you'll notice, the first two are sums of things getting squared. Now they have things in front of them, namely this ni here and this ni minus 1. But the SS stands for sum of squares. Now you might be saying, well, this SST is not a sum of anything. It's just this times that. It actually comes from a sum of things, and this is the shortcut for calculating it. If you really want to read all the gory details, I'm pretty sure I go into the details in the videos, but if you want to see all the gory details about all the sums of squares, I'm going to recommend, wait, wrong version of the book. I still have the book open. I do. My Stats 1 class. Give me 1 second to get all the way to the correct page. This is in chapter 8, so I might as well do this. Where am I? Come on. I always go to a place where it doesn't say what chapter I'm in. Go, 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 go. Whoa, whoa, whoa. Oh, that's just chapter 7. There we go. Why was I doing this? I was doing this to show you the pages that if you really want to get into the math behind all those SS formulas, you kind of have to go to the end of the section where they say, oh, by the way, here's the formulas. Well, there's the table we're completing. I just want to show you where the pages are. Here we go, ANOVA calculations. This begins on page 550 of your book. If you really want to get into the get your hands dirty math where everything comes from, there's the formula for SST, SS total. It is a sum of squares. Basically, what SS total measures is for each individual number in all the samples, how far do they deviate from the grand sample mean? In other words, if we forget the fact that these samples all came from different populations and dumped them together in one gigantic mess of values from multiple populations, let's figure out the average of everybody and figure out how far off average everybody is, square them and add them. So it is a sum of squares. For SSG, which is variability between groups, we do kind of the same thing, but we take each individual value and see how far it deviates from the grand sample mean, as opposed to, I'm sorry, we take each individual sample mean and see how far it deviates from the grand sample mean, square it and multiply it times that sample size. And then the other one, SSE, is the how far does each individual value deviate from its sample's mean, square them and add them. So all of these SS's are sums of squares, and there's actually some algebra that can show you that this guy up here is the sum of those two things there. But that's what the SS stands for. I'm not going to ask you to do much of that outside of the one time in the homework. The second column in your ANOVA table is titled SS, one for groups, one for errors, and one for total. Now, these values do have those nasty formulas that are the sums, but the good news is of these values, they will probably be given. So you don't have to actually calculate them. In fact, if you were to look in the homework problems in the book, you are not ever asked to actually calculate those. They are handed to you. Here's your SS's. Well, at least two of them, because the same thing as the first column, this column is additive. The SS column is additive, meaning that the first two will add up to the third, meaning you don't ever have to be given all three of them. You only need to be given two of them. And then you can add to get the third one if you're missing the total, or subtract to get the third one if you're missing the first or the second one. So we won't be doing much of that. And on your test, you will be given 2 out of the 3 SS values so that you can calculate the third. All right, so let's pretend that we get these SS values, whatever they mean and wherever they come from. Your third column loses the bottom row. And the reason it loses the bottom row is because it is not an additive thing anymore. I'm not going to get into the details as to why we moved to this third column, but MS stands for mean sum of squares. There's an MS for the groups and there's an MS for the errors. If you watch the videos in their entirety, the story goes like this. We're measuring variability between groups here. We're measuring variability within groups. And give me 1 second to make sure that I just said the correct within and between at the right time. I know visually there's a reason you say between groups versus within groups when you have 2 pictures and you're looking for how much overlap they have. But yeah, it was between. But when you are measuring variability between groups, which means when we are looking from a sample that this person took from a population versus a sample that person took from a population, how much variability are between the samples that we took from the same population, and compare it to the variability within groups. I think I said that backwards again. When we compare the variabilities within groups versus between groups, the problem is those sums weren't equally balanced. I'm not going to go back to the original sums, but one of these sums had 1 addend per sample, and the other one had 1 addend per individual measurement in all the samples. So it's not a very fair battle because you're adding a lot more values down here than you are up here. And so the way that you put them on a comparable level is you divide them by their degrees of freedom. The formula for MSG, MS groups, is SSG divided by its degrees of freedom. And I didn't leave enough room there, but when I say divided by degrees of freedom, I mean for that row. And for MSE, it's SSE divided by its degrees of freedom. So in other words, when it comes to filling out this column, it's a division problem. For the top one, you take this divided by that. For the next one, you take this divided by that. And when we do this, it's actually really easy to do. When I have your formula chart, it doesn't just say DF, it says DF groups and DF errors to let you know that you're not leaving that row. And then once you calculate both of those MSs, then and only then do you finally get to your test statistic, which kind of merges those two cells. It blurs the line and it's one giant cell. This F that you calculate, this is your test stat. And the formula for the test statistic is really easy. The formula for the test statistic is MSG, meaning the answer we got in the cell right here, divided by MSE. We're comparing mean sum of squares, so the answer that we got right there. And that actually completes the ANOVA table. Now, in some of them, you will also see, and I'm going to change colors. In some of them, you will see another column that has a single value, and it will be the p-value. I got to write that a little bit better. It might just say p, or it might say p-value. It should say p-value. If it just says p, shame on it. But the p-value, I'm going to put an asterisk there and go down here and define what that asterisk is in the same color. The p-value is the area of the right tail cut off by the test statistic. And there's a way to get a range of values. I don't like that color green. Hold on. There, that's a little bit easier to see. But the p-value is the area of the right tail cut off by the test statistic. Really, that's all a p-value is. In a hypothesis test, a p-value is just the area of the tail or tails cut off by the test statistic. The problem with finding the p-value is you usually need technology to get a good estimate for it. If you're just using a table, there is a way to get a range for the p-values, which might work just as well. I'll show you that when the time is right. But when you're asked to complete an ANOVA table, you are given some of the information to set it off, and then you just go left to right. It's actually much easier to do than it may seem right now, because all I've done is write a bunch of words and symbols up here. So I want to show you how to complete an ANOVA table by looking at the one in your homework. So I'm about to give you answers to some of your homework questions. All right, so let's go find that homework. Where'd the homework go? Is it here? Nope, here. That's it. Whoop. I forgot I had it pinched in. Okay, so let's go up to, let me see if I can find one here. Here it is. All right, so this is, all of this is questions 14 through 20. Complete the ANOVA table, given that there are 5 groups with a grand sample size of 105. Instead of me redrawing this table in the Zoom presentation, I'm just going to write on it inside of this PDF. So if you're taking notes, you might want to take a moment to sketch the table that you see here. And I forgot to tell you that we can title the first column source, the source of variability, if you will. And notice that I spotted you the SSG value and the SST value, the sum of squares for the groups and the sum of squares for the total. I'll give you a second to jot that down. And what we're going to do is use the information that's given above the problem, which you can't see right now, to fill out the rest of the numbers in here. You will have a question on your next test like this one, where I give you a mostly empty ANOVA table and give you enough feeder information, if you will, to complete it in its entirety. If you're still copying it, by all means, keep copying it. But I'm going to go ahead and get this started. All right, complete the following ANOVA table, given that there are 5 groups with a grand sample size of 105, round to 2 decimals is necessary. And all the questions below it are asking is, what are all the values you're going to get inside of there? So I don't need to focus on those questions down there. There are two key pieces. That's a bad phrase to spoonerize, if you know what a spoonerism is. There are 2 key pieces. Spoonerism is when you switch the initial sounds of 2 words. Oh, that made me a really funny joke, but I can't think of it. All right, so let's go and pick out the information we're given. We're started with 5 groups. So when we're told that we have 5 groups, that's what the K equals. And oh, I remember it was. Hold on. K is 5. It's the number of groups. And the grand sample size is 105. I just noticed that one day and it blew my mind. Grand sample size. Now the word grand is in front of it over here, so I owe it to underline that. The grand sample size is 105. That's the lowercase n. So we have everything that we need to completely set off this table. Now I don't have room to write the formulas inside of the table, so hopefully you saw them earlier and had them written down. Come on, zoom in. There we go. Whoa, that's a little bit too much. So I'm getting some lag here. All right. The formula for degrees of freedom for group was K minus 1. Pinch that a little bit more. So what is the degrees of freedom for groups? In other words, what goes right there? 4. 5 minus 1 is 4. So is everybody okay with where that came from? Okay. The formula for degrees of freedom for errors is n minus k. N minus k is 100. Now, for the total, you can either use the formula n minus 1, or remember that this column is additive, meaning that the top 2 add up to the third one. 100 plus 4 is 104. Now, we don't actually use the total degrees of freedom, but sometimes we know that and not one of the others. And so we can subtract to find the one that's missing. As far as the SS column is additive. First one plus the second one equals the third one. So if you're missing the first or the second, you can just subtract and get 4,000. So before we go any further, does anybody have any questions about where any of those numbers came from? Oh, and I want to point something out before we finish this, looking at the book, which is here. They have all the formulas capsulized, and here it is, capsulized inside of an ANOVA table. Don't worry about this notation over here. It's not the notation that I choose to use. But what you see here is what will be on your formula chart. It's K minus 1 here, A minus K there, A minus 1 there. MSG equals this over that. Now, they do explicitly say it's K minus 1, but it's just the degrees of freedom over here. Same thing there, it's N minus K, it's just the degrees of freedom over there. But I will provide you all of these formulas inside of the ANOVA table as part of your formula chart. Okay, so let's go back to this. All right, so, and this is what I was saying about the MSs. To find the MSs, all you have to do is divide. All you have to do is divide the SS, hold on, divide this guy by the guy in front of it. So 1,000 divided by 4 is exactly 250. And then the other one is 4,000 divided by 100 which is just 40. So that's how you get the MSs. The MS is the SS divided by the degrees of freedom. Okay, easy calculation. And then your F statistic is just the ratio of your MSs. In fact, it's practically staring at you. That looks like 250 over 40 because it is. 250 divided by 40, I think is 6.25. Okay. No. Yes, divided by 40. I said 40, but I wrote a 4. Is 6.25. And so if we were doing a hypothesis test and we were at the point of calculating your test statistic, that 6.25 is your test statistic. So individually, the calculations aren't that hard. There's just a bunch of them in a row, from samples and sample sizes and SSs all the way to your test statistic, the value for F. Does anybody have any questions about completing that table? It's not a difficult thing to do if you're given 2 of the 3 SSs. Otherwise, it's a pain in the posterior. Okay, let's go back to the Zoom recording. I'm sorry, does anybody need anything else that's written up there? I know I can tell some of you are still writing it, so I'll pause for a second. And also remind you that there were some things that we talked about last time that I haven't talked about yet today, like which of these pictures provides stronger evidence that population means are different or equal, whichever one you want to choose. And the one with more overlap provided stronger evidence of equal means, and the one with less overlap provided stronger evidence of different population means. But all of that was just a motivation that led to measuring variability, calculating SSs that took us here. So I skipped a lot of the details in between. Want to see all the details? Watch all the videos. All right, so that's how we calculate the test statistic painstakingly. That's not that bad. All right, now the good news is, and let me see if I can find a real quick example of it. The good news is, in real life analysis of variance, you don't even do this. Let me show you what happens when you use technology to do the dirty work for you. Let me zoom out for a second. Words. All right, so here's an example, and this isn't one of your homework questions, so I'm not going to worry about the context. It is a long setup for the context, but if you can go into Excel and drop sample number 1 in one column, sample number 2 in another, sample number 3 in another, however many columns you have, you can highlight, click, and Excel will do the dirty work for you and provide computer output, complete with everything. You don't have to calculate a thing. You can verify. Well, if I divide this 27.04 by 3, I'll get this approximately. And if I divide this by that, I'll get this approximately. And if I divide these two, I'll get that approximately. And you can check that the first 2 columns are mostly additive. I say mostly because sometimes they're not precisely additive due to rounding errors. Like this column here, I can tell right in the last digit, 4 plus 2 is not equal to 5, but I would attribute that discrepancy to rounding issues. So sometimes you don't even have to complete the ANOVA table. If you're doing real life statistics, you just have to get the data into Excel and ask it to create the ANOVA table for you. At some point, I'll probably do that to illustrate it. Takes even all of that work out of it. So that's convenient. All right, let's get back to the to this. All right. So we calculate a test statistic, and the rest of the hypothesis test is easy because you know what happens next. Okay, we're doing a hypothesis test. We state the hypotheses, we calculate, we determine the regions and the critical value, then we calculate the test statistic, and what happens after that? What's the 4th step? Thank you. Make a Q decision. Now that's what you do in poker when you're dealt ace queen. Make a decision, but this is the same as before. I'll just remind you, if the test stat lands in the rejection region, but because this is always a right tail test, we can be even more specific. In other words, if the test stat is greater than the critical value, because if you're right tail, that's what it means to land in the rejection region. Reject the null, the nil. Otherwise, do not reject the null. So it wraps up real quick, like most hypothesis tests do. All right, so let's, I'm sorry, any questions about making a decision? Because it hasn't changed since day one. Okay, all right, let's go back to the homework, shall we? Which was here. All right. So I literally just answered all these questions, 14 through 20. So if you didn't write them down, I have no sympathy for you. Now, armed with the information I just showed you and the knowledge that this should say SSE, you can now do this. I'm not going to do it for you because I'm not going to do all of your homework, but we can talk about it. Let's just get our minds in the context. The light bulb manufacturer wants to know if each of K equals 3 assembly lines are producing light bulbs with the same mean lifespan. 10 light bulbs are sampled from each of the 3 assembly lines. So they're setting up the 3 populations of light bulbs that come from this assembly line, from that assembly line, and from that assembly line. 10 light bulbs are sampled from each of the 3 assembly lines after testing each bulb for lifespan. So they're gathering their sample values. The values of SSG and SSE are calculated as those 2 numbers. Perform an ANOVA test at 5% to determine whether the assembly line produces light bulbs with the same mean light span. Bless you. State the hypotheses. Now, I know we have a couple of generic approaches to stating the null and the alternative hypothesis, but within the statement of the question is the perfect wording for one of the hypotheses. Does anybody know where that is? Within the statement of the question, there's a perfect wording for one of the hypotheses. Right after K equals 3. Assembly lines are producing light bulb. Okay, that's not where I was looking with. That is good. The assembly lines are producing light bulbs with the same mean lifespan. I was actually looking down here. Well, that says the exact same thing. Okay, that says the exact same thing. But you know, when you see a wordy word problem like this, especially in a hypothesis test, there is a good chance that one of your hypotheses is there for you. So if this were a test question, I would say state the hypotheses in context of the problem. The one that's highlighted, is that the null or the alternative? It's the null, because remember what we're testing is all the means are equal, at least 2 of them aren't. And that highlighted part says that they're all the same. So that would be the null hypothesis. If I wanted to state the alternative, I could say at least 2 assembly lines produce light bulbs with different mean lifespans. Or you could also say not all of them have the same mean, but you got to be careful. When I say not all of them have the same mean, that doesn't mean they're all different. Not all of you are the same age. Can we agree that that's true? Does that mean all of you have different ages? Probably not. Anybody here 18, 19, 20? Aha! 3 of you have the same age. So saying not all of you have the same age is not the same as saying all of you have different ages. So you could say that the alternative is not all assembly lines produce light bulbs with the same mean lifespan. All right, so I just kind of verbally gave you the answer to number 21. For 22, to determine the critical value, that's where you would use the table. Critical values are not found from formulas. They are found from tables. Test statistics are found from formulas. So you would just look up the correct page, the correct column, and the correct row. So let's just talk about it real quick. Which piece of information in the problem is going to be used to choose the correct page on the F distribution? And I'll put the F distribution back up here for a second and scroll through it just so you can remember what all the pages look like. Here's the first page. Here's the second page. Here's the third, and then there's the fourth. So I reiterate the question, what piece of information in the problem tells you which page to go to? The significance level. And from that point forward, you have to choose the correct column and the correct row based on the degrees of freedom for the numerator, which is k-1, and the degrees of freedom for the denominator, which is n-k. Do we have an n? It's 30. The n was not explicitly stated, it was implied. The n is the grand sample size, the sum of all the individual sample sizes. We took 3 samples of 10 light bulbs each, so you have to infer from that that n is equal to 30. So y'all see where the 30 came from? Okay, n is the grand sample size. So the sum of all the different sample sizes. We were told that we took 10 light bulbs from each of the 3 assembly lines. So from this line, I took 10 light bulbs. From this line, I took 10 light bulbs. From that line, I took 10 light bulbs. So altogether, 30 light bulbs. That's where the 30 came from. Just remember, the grand sample is as if you were erasing what separates the populations. Oh man, look at all these light bulbs. I don't know which one they came from. Oh, well, I just got 30 light bulbs. Yeah, like that. Okay. All right. Okay, so we have the n, we have the k, so we can calculate all the things that we need to determine the critical value. Now for the test statistic, that's where you complete the ANOVA table. And notice that I did say to arrive the desired answer that the quiz in Canvas is waiting for. Then you round your answers for both MSG and MSE to 2 decimal places before calculating F, which you should also round to 2 decimal places. Translation, every time you divide in the table, round to 2 decimal places. Yeah, for that problem. And at that point, it's easy to make a decision and then make your conclusion. The one thing we haven't talked about is the p-value approach. We haven't talked about it much, and I want to show you how to play it out. Before we do that, does anybody have any questions about anything that I said for this batch? Okay, so here's what I want to do to wrap up the class. I want to talk about the p-value approach and then go backwards through the homework to see if there are any loose ends I need to tie off. All right, so p-value approach. You know, I've been kind of postponing it and et cetera, et cetera, et cetera, but now is the time for us to start diving into the p-value approach. Because as we are given computer outputs, in other words, somebody crammed numbers into Excel or somewhere else and spit out a computer output, which will frequently contain the p-value. So let's talk about the p-value approach. First off, in a hypothesis test, the p-value, and I've said this already, but I'm going to type it. The p-value is the area of the tail, parentheses, the area of the tail or tails cut off by the test statistic. And the reason I say plural is if you're doing a two-tailed test, your test statistic will only cut off one tail. So normally when it's a left tail or a right tail test, it is just the area of that tail. So I need to distinguish this real quick. That's not what I wanted to do yet. I didn't want red there. I want red here. If it's a left tail test, and this is your test statistic, then the p-value equals that area. I do want to type that in red and smaller font. It's the test statistic, because the area cut off by the critical value is just the significance level. Okay, but I'm glad you asked, because I had to pause and make sure I said test statistic at the right time. The p-value is the area of the left tail. So if it's a left tail test, then the p-value is just the area of the right tail, the area of the left tail, excuse me. If it's a right tail test, which ours will always be, then your test statistic cuts off a tail, and the p-value is the area of the right tail. But the key thing is it's the area of the tail cut off by the test statistic, not cut off by the critical value. Now, if you have a two-tail test, I'm going to do it in green over here just so it doesn't blur with the other two. But if you have a two-tail test, then it's a slightly different story. Because when you have a two-tail test, you still have just one test statistic. But it was a two-tail test. So to make it comparable to the significance level, which represents in a two-tail test would be the area of the two tails, the p-value is twice the area of that tail. And in a two-tail test, it might be on the right, it might be on the left. Because remember, a two-tail test happened when your alternative said not equal to, which means it could be on either side far enough away. If you drew the regions in a two-tail test, you would have two critical values. It cuts off a left tail and a right tail. But when you get the test statistic, you only get one of them and it cuts off one tail. So it's not fair to compare one tail to two tails. So when you do the p-value approach for a two-tail test, the p-value is twice the area of the tail. This is another reason I don't like using the p-value approach, because you have to ask yourself, is the p-value the area of the one tail, or is it twice the area of the one tail? Well, it's twice the area when it's a two-tail test. But the p-value is the area of the tails cut off by the test statistic. So if you think about it, we get the test statistic, and then we got to figure out what's the area that it cuts off. That's different than saying, I know the area it cuts off, let me find the critical value. So it's doing backwards what we do on the critical value. So that's what the p-value is. And then once you get the p-value, your decision is based on how the p-value compares to the critical value. Man, if I could learn to type, I could be one of the fastest typers. Your decision is based on how the p-value compares to the critical value. No. No. No, not how it compares to the critical value to the significance level. There is no critical value in the p-value approach. Otherwise, we do the critical value approach. You don't do the critical value, you skip it and go right to the test statistics so that you can get to the p-value. Your decision is based on how the p-value compares to the significance level, which is the Greek letter alpha, but I can't type the Greek letter alpha, so I'll just type the word alpha. If the p-value is less than the significance level, that means you reject the null. If the p-value is greater than or equal to, and please forgive me for typing greater than or equal to that way, I cannot type the line underneath there. But if the p-value is greater than or equal to alpha, means do not reject the null hypothesis. When I first taught statistics, I didn't like this part of the p-value approach because it seemed arbitrary. Why do you say reject when it's less than the significance and do not reject when it's greater than the significance? Because the p-value actually has another meaning. Visually, it's the area cut off by the test statistic, doubled if it's a two-tailed test. But what the p-value really measures, and this author doesn't get into it because they don't get into probability, what the p-value really measures is the probability your sample would occur if the null hypothesis is true. So the P in p-value actually means probability. And it makes a little bit more sense now to say this thing, because think about what happens if your p-value is too small. All right, we have a 5% significance level. All right, our p-value is 1%. Our p-value says, yeah, if your null hypothesis is true, then the probability of seeing what we saw in the sample was 1%. That's highly unlikely to happen. I guess our null hypothesis was wrong. So if you think about p-value as the probability of your sample occurring, what that highlighted thing says is if your probability is too small, you shouldn't have seen that happen if the null hypothesis was true. So I guess the null hypothesis isn't true. All right, last thing I want to show you is how to get the p-value from the table. And that's the reason I don't like focusing on the p-value approach too much. I know we only have 4 minutes, but we didn't meet Monday. So give me 4 minutes. All right, to get the p-value from the F table, the best we can do is narrow it down to a range of values. For example, and I'm going to borrow the values that we got from the homework table in questions. I don't remember which questions it was. It was like 14 through 20, wasn't it? Okay. In questions 14 through 20 on the homework, we had degrees of freedom for the numerator equals, that was k minus 1. I believe k was 5, so it was 4. And we had degrees of freedom for the denominator. That was n minus k, which was 100. And we had a test stat of F equals, it was 6.25, wasn't it? Okay, so here's how you would get a range of p-values. I'm going to go ahead and set it up from the table. And this is really why I don't like the p-value approach without technology. If we go to the distribution, and this is really tricky with the F distribution. Let's start by looking at the correct column and row on each page. 4th column, 100th row, quote unquote. Oh no, it doesn't go that far. All right, infinity row to the rescue. Here is the F. Yes, there's the F value with the correct degrees of freedom when the significance level is 10%. Our F, our critical value was 6.25. Okay, let's go to the next page. Same column, same row, bigger F, but not big enough. Our F was 6.25. All right, next page, same column, same row, bigger F, but not big enough. Okay, next page. We need a bigger F. We're on the last page, same column, same row, slightly bigger F, but still not big enough. So here's what we know. With the correct row and column, as we went from page to page, as the significance level dropped, our F was getting higher, but it didn't get high enough. We would need to go to more pages to get to 6.25. And as we go from page to page to page, the significance level is dropping. The area is dropping. Forget that it says significance. Think about it saying area. So with the correct row and column from page to page, what we're looking for is getting larger, but it's not large enough. If we had more pages, we would have to keep going and the area would keep dropping. So all I know is that it's on a future page that we don't have, and this number is going to keep getting smaller. So all I know about the p-value is that it's less than that. Almost done, folks. Give me like 30 seconds. I know it says 7:05. All right, so the range of p-values is, and I shouldn't have said a range of p-values because what I thought I was going to say is it's between these two numbers, but I know that the p-value is less than 0.01 because we didn't find the F that we were looking for and we hit the last page. So we'd have to go further, get a smaller and smaller area, but this is good enough because if I know my p-value is less than 1%, that it's definitely less than 5%. And assuming that our significance level was 5%, then we have a p-value less than the significance level and we reject the null hypothesis. Okay, do me a favor, go through the homework, and if there's any loose end that needs tying up, let me know so that I can tie it off for you, okay? And Monday will be the last opportunity to ask questions on that homework in class. Cool, and we're done. No one joined the Zoom? Oh, well, they can watch it later. Yes, ma'am. I noticed that. It was p-value less than alpha is reject. P-value greater than or equal to is do not reject. Basically, what the significance level says is this is the lowest probability we'll accept without rejecting the null hypothesis. So if our p-value, if our probability of the sample happening goes below that, I'm sorry, that was so unlikely your null hypothesis must not be right. So 5% is the lowest probability that we would accept. And it's very rare, it might even be technically impossible for the p-value to exactly match the significance level. The calculations are just so, yeah, it would be statistically impossible for that to happen. Okay. Yes, sir. Okay. Could you have it done by this coming Monday? Make sure you send me the Excel stuff before Wednesday and just bring the paper part on Monday. Okay, yeah, digital stuff by the due date and then paper by Monday. Well, do you know what they are?